application of genetic algorithms for optimization of salesman's tasks and their modeling by sequential selection. Abstract. Lately, artificial intelligence has been becoming more and more popular, but at the same time, a stereotype has been formed that AI is only based on neural networks, even though a neural network is one of the numerous directions of artificial intelligence. The aim of this paper is to bring attention to other directions of AI, such as genetic algorithms, study the process of solving the traveling salesman problem, or TCP, via genetic algorithms, or GA, and take a look at the problems of this method. The genetic algorithm is a method for solving both constrained and unconstrained optimization problems that is based on natural selection, the process that drives biological evolution. One of the common problems in programming is the traveling salesman problem. There are many various methods that can be used to solve it, but the one we are going to take a look is the genetic algorithm. The aim of the study is the most efficient application of genetic algorithms in the traveling salesman problem. Introduction. One of the common problems in programming is the traveling salesman problem. There are many various methods that can be used to solve it, but the one we are going to take a look at is the genetic algorithms. The aim of the study is the most efficient application of genetic algorithms in the traveling salesman problem. Lately, artificial intelligence has been becoming more and more popular, but at the same time, a stereotype has been formed that AI is only based on neural networks, even though a neural network is only one of the numerous directions of artificial intelligence. The aim of this paper is to bring attention to other directions of AI, such as genetic algorithms, study the process of solving the traveling salesman problem via genetic algorithms, and take a look at the problems of this method. The origins of the traveling salesman problem are unclear. A handbook for traveling salesmen from 1822 mentions the problem and includes examples of tours through Germany and Switzerland, but contains no mathematical treatment. It was first concealed mathematically in the 1930s by Farrell M. Flood, who was looking to solve a school bus routing problem. Kessler Whitney at the Princeton University introduced the name traveling salesman problem soon after. There are many methods of solving this problem. Some of them give exact results, others only approximate. One of the more interesting methods is the method of route optimization with the use of genetic algorithms. First experiments, which involved simulation or rather simulated evolution, were conducted by Niels Al Baricelli in 1945. Later, they were also conducted by Niels Al Baricelli, Ingo Rechberg, and Hans Paul Schwefel. Thanks to them, artificial evolution became a well-known optimization method. Theoretical basis. The traveling salesman problem is a problem of finding the fastest, or rather most efficient, route between n cities when the route must go through every city only once. If the problem is presented in the form of a graph, then the answer will be the form of the Schroeder's Hamiltonian cycle. The traveling salesman problem can be presented as a graph. In this form, the represented cities are displayed as vertices, and edges represent the criteria of profitability, in other words, distance or time. Asymmetric and symmetric problems. The catch in the asymmetric problems is that the profitability between the cities is dependent on the direction of the edges, whereas the symmetric problem, the directions has no role. There are two main groups of methods for solving the traveling salesman problem, which can be combined. First, precise. They find the precise, optimal solution to the problem, but it takes a long time to calculate. The second one, heuristic. They give an approximation of the optimal route, but take notably less time to calculate. Genetic algorithms are generally more efficient than the complete vocabulary, as there is no need to go through all possible combinations. At the same time, genetic algorithms are heuristics, which do not guarantee a precise solution, but only the best possible approximation with the given amount of time, or iterations. Analytical part. The complexity of using this method is that the usage of regular crossovers or mutations is not possible. In classic genetic algorithms, crossovers are generally presented as simple combinations of different parts of the parent chromosomes. The example of this can be seen in an image below. The first strategy, simple. As was mentioned before, in order to avoid getting to a same city twice, merely differently combining halves of parent chromosomes will not be sufficient. The simplest way to resolve this is to change the city, which is repeated, to a city that is not present. but at the same time, this method entails the fact that each possible descendant may have several options. The second strategy, cycle. The previous strategy was based on a basic crossover which had to be improved so that the children could form a Hamiltonian cycle, which in turn would create a large quantity of children variations. If we take the pre-made directions of movement, which were taken from parent chromosomes, then there would be no reason to correct the children. As a result, by using this method, we will acquire a wanted amount of children and will not be dependent on the amount of repeating cities. The idea of this strategy is that the combination of parent genes should immediately form a Hamiltonian cycle. In addition to making sure that the child chromosome would not repeat its parent, it is necessary to limit the length of parent chromosomes from which the child will be built. The third strategy, nearest. Based on the second strategy, a new, more efficient crossover can be created. In the second strategy, we have up to 4 different moves, and if the most efficient one can be chosen, then the runtime of their algorithm will be substantially improved, while at the same time drastically decreasing the number of generations needed and increasing the time designated for computing in a single generation. In order to make sure that the complexity of the algorithm will not increase, the restriction regarding copying the father's sequence shall be ignored. As a side effect, this creates an issue where the child can become a carbon copy of the parent, yet it can be solved by either mutating such child or by banishing it from the general population. Results. We will conduct a study on equal terms for each one of the methods. For this, we shall use the same map and the starting generation. Analyzing the efficiency of the crossbreeding method, we will conduct a study on 50 generations, with the size of each being 100 individuals and the possibility to reproduce in the 90% of the population. In the first method, the most efficient route is NASBEGTKLDFOMRCPIHQ, figure 8, where its length is 100.69 and the runtime is 5,501 milliseconds, or 110 milliseconds per iteration. In the second method, the most efficient route is CAHRNQSTKJBEGLFIDMOP, figure 9, where the length is 118.90 and the runtime is 3865 milliseconds or 77 milliseconds per iteration. In the third method, the most efficient route is HCRMPOIFDLJBEKTGSQAN, figure 10, where the length is 77.68 and the runtime is 2341 milliseconds or 46 milliseconds per iteration. As we can see, the third algorithm has the best runtime and gives us the shortest final route. The second algorithm is average in both runtime and final route, and the third one has the worst runtime and returns quite mediocre results. An analysis of the approximation to the optimal solution. As we can see from the chart, the third method gives us the best results, and the results of simple and cycle methods are actually quite similar. The nearest algorithm has the largest decline, and because of that, it needs fewer generations to achieve the optimal solution. Cycle gave us some interesting results. It has a jump-like approximation, and it happens much less often than in other algorithms. As a result, the best fitted individual survived for much longer compared to the other simple and nearest algorithms. As we can see, genetic algorithms are a nice way of locating the best possible solution. They have a rather short runtime, where one iteration can take between 64 to 110 milliseconds in 20 cities. We took a look at 3 methods of crossbreeding, and from them the most efficient one was the third one. This is thanks to the fact that the third one has one special feature from the nearest neighbor, which in turn makes every child have a better adaptivity score than its parents.